So we are going to look at another limit problem. When we started with the graph on this one, we've got z equals x to the fourth over the quantity x to the fourth plus y cubed. And 0, 0 is definitely not in the domain of that function. And when we look at this graph, we see this really strange behavior going on right here when our xy points are close to 0, 0. We've got z values here. We seem to have z values down here. So based on this picture, we should expect that the limit does not exist as xy approaches 0, 0. So let's go over to the board and see if we can show that. Okay, so here I've got our function that we just looked at. F of xy equals x to the fourth over x to the fourth plus y cubed. 0, 0 is not in the domain of that function. You might notice that there are also many other points that are not in the domain of this function, such as 1, -1. Some of the previous examples we've looked at, only 0, 0 has been excluded from the domain, but this has quite a few points, infinitely many in fact, that would be excluded from the domain of this function. But certainly, because 0, 0 is one of those points, this is an interesting limit to consider. So previously, when we looked at some limits where we thought that the limit did not exist, the strategy we looked at last time was to use polar coordinates. And there were two things that made polar coordinates work really well in the previous problems where we've used that. One is that we're approaching 0, 0, so we still have that going on here. But the other was that we had x squared plus y squared in the denominator, and that became r squared, and we were able to let r approach 0. So you might think through polar coordinates here. I would have to substitute x equals r cosine theta and y equals r sine theta. And I'm going to get a big expression here in the denominator that involves r's and thetas. Might be a little cancellation that I can do with some r's, but they're not going to completely cancel out. And so while you could convert to polar coordinates, it is definitely not as nice for this problem as it was for the previous problems. But even when we did convert to polar coordinates, remember what we had to do at the end. We had to really show that when we ended up with an expression that involved theta, that if we were trying to show that limit did not exist, we wanted to show that we got different values along different paths of approach. And actually, we can do that in just xy coordinates on this one. Remember, we already looked at the graph, so we have an indication that probably this limit does not exist. We're just going to show it. So I'm going to think a little bit about the geometry here. I'm also going to use some slightly different notation than our textbook does, so I'll talk about that a little bit. But what I've graphed here is just an xy coordinate plane, and I just want to think about paths of approach that approach the point 0, 0. And so the two easiest paths of approach are coming in along the x-axis or along the y-axis. So let's come in along the x-axis first here. All right, so I'm going to write down the limit notation for a path of approach that would be coming in along the x-axis. And the picture is helpful here because when you think about this picture of an xy coordinate plane and think about the x-axis, you can see here that if you're coming in along the x-axis, every point on that x-axis has a y-coordinate of 0 that is equal to 0 and an x-coordinate that's just approaching 0. So when I come in along the x-axis, the y's will be actually equal to 0 and x will be approaching 0. So y will actually equal 0 and x will just be approaching 0. So I can rewrite this function here. I get this limit to be the limit as x approaches 0 of x to the fourth over x to the fourth plus 0 cubed. Remember, the y is actually equal to 0 and x is just approaching 0. Okay, so this denominator just becomes x to the fourth. And this function here simplifies. So I'm not really going to worry about my limit quite yet. I'm just simplifying. I substituted in y equals 0 since I'm taking that path of approach. And now I'm just simplifying. And this function simplifies to just 1. So I get the limit as x approaches 0 of 1, which is 1. So along this path of approach, if we look back at the computer graph, we would expect to see z values that are getting closer and closer to 1. Again, having looked at the graph, I know that this limit appears to not exist, so it's just a matter of showing that. So here I've got a limit, what happens when I'm approaching along the x-axis, and then kind of the next easiest path of approach to think about is maybe the y-axis. So if I come in along the y-axis from both above and below, for every point that's on that y-axis, I've got an x-coordinate that is equal to 0 and a y-coordinate that is not, and that y value is approaching 0. So coming in along the y-axis, right, so x will be equal to 0 and y will just be approaching 0. All right, so I'm going to essentially make those same strategy here of substituting in for the one that's equal to 0 and then letting the other one actually approach 0. So my original function, I will have limit as y approaches 0 of 0 to the 4th over 0 to the 4th plus y cubed. All right, so when I simplify this, the numerator is just 0, and the denominator is y cubed. Okay, so it's important to understand here the difference between something being actually equal to 0 and something just approaching 0. In Calculus 2, or maybe even before that, you might have talked about limits that are indeterminate forms, where you have something approaching 0 over something that's approaching 0. That is not what we have here. Right? This is an indeterminate form, and a limit that has this form could have any kind of answer. It could be 0, it could be infinity, it could be any real number, it could have a limit that does not exist. That is not what we have here. This numerator is actually equal to 0, and the denominator is expressly not equal to 0. If you go back to that definition of limit and remember that definition of limit, part of that definition would say that here y needs to be arbitrarily close to 0, but not actually equal to 0. So my numerator is equal to 0, and my denominator is not equal to 0. It's close to 0, but not equal to 0. So when you have a fraction where the numerator is actually equal to 0, and the denominator is something else, just close to 0, that fraction is actually equal to 0. Right? So this is different when we have something equal to 0 versus something approaching 0. So this fraction just simplifies to 0. The limit as y approaches 0 of 0. I just simplified this fraction. This is 0. And then as y approaches 0, 0 stays 0. Okay, so I have two different limits along two different paths of approach. So my function is approaching different values along different paths of approach. One is not equal to 0, so I have different limits along different paths of approach. So I would say that this original limit does not exist. And here is all of my work to justify it. Our textbook calls this the two-path test to determine or to show that a limit does not exist. I want to emphasize, though, that if I had gotten the same answer for both of these limits, that would not be enough to show that the limit does exist, because you really have infinitely many paths of approach to check. So we will look at another example where when we try these kind of first two easy paths, we get the same answer, but it's very obvious from the picture that that limit does not exist. And so then you have to go looking for more creative paths to show that that limit does not exist. But essentially, the key idea to get from this example and the previous video and also the next video is this idea about showing that a limit does not exist. One way to do that is to show that you get different limits along different paths of approach. So the question is, are they easy to figure out two different paths of approach that give you different limits? Or do you have to be a little bit more creative in finding paths along which you get different limits? So we'll look at one of those in that next video.